Can we time travel through black holes? You've hit snooze one too many times, missed your meeting, and now you're wondering, could I just jump into a black hole and rewind the day? You're not alone in that wonder. This is a real question physicists have dared to poke with a very long, very nervous stick. Black holes warp time, space, and logic itself. So can they let us travel through time, or will they just crush us into noodle soup? What even is time travel? Wishing you could go back 5 minutes like in a video game is the emotional heart of time travel. But scientifically, well, it's not that simple. Time travel splits into two branches, forward, which we know can happen, and backward, which breaks reality's kneecaps the moment you try to make it work. Forward time travel. Einstein gave us the keys to future hopping with his theories of relativity. Time, it turns out, doesn't tick at the same rate for everyone. If you move fast enough, really fast, close to light speed fast, time for you slows down compared to everyone else. Let's say you hop on a spaceship going 99.9% the speed of light. A few months pass for you on board, but back on Earth, years, maybe even decades, might tick by. It's like skipping through time, one fast-forward jump at a time. The ISS already does this. Astronauts age milliseconds slower than we think thanks to their orbital velocity. It's barely noticeable now, but the effect scales. Then there's gravitational time dilation, more like potato. The closer you get to a massive object like a black hole, the more space-time warps and the slower time flows for you. In both cases, you're not changing time, you're experiencing less of it while others keep going. Backward time travel. Now let's talk about the fun one. Time travel to the past. This is where the math gets greasy and the logic shatters like a cheap wine glass. See, general relativity technically allows for backward time travel. There are solutions to Einstein's field equations, like rotating black holes or wormholes, that suggest closed time-like curves or CTCs. Think of a path through space-time that loops back on itself like a snake eating its own tail. You could, in theory, follow that path and end up where and when you started. Imagine boarding a cosmic roller coaster, flying through a wormhole, and landing 5 years ago at your own birthday party. But now you've got problems, serious ones, because if you're back in time, you might change something. Maybe you trip over your past self, or worse, stop your parents from meeting. Congratulations, you just hit the grandfather paradox. If you stop your own birth, how did you exist to go back and stop it? This is where time travel slams into the wall of causality. Backward time travel breaks the rule that cause comes before effect. Suddenly, your actions ripple backwards, and logic collapses in on itself like a black hole with stage fright. Some scientists try to patch this up with ideas like the Novikov self-constancy principle. You can go back in time, but you can't change anything. Everything you do in the past already happened. Others punt the problem to the many worlds interpretation, meaning every time you alter the past, you branch off into a new timeline, like snipping a thread and tying it to a new future. Neat, chaotic, unprovable, yet mathematically possible. How black holes break time. If space were a trampoline, black holes aren't just bowling balls, they're wrecking balls dipped in lead and flung by a god with bad impulse control. A black hole forms when a star collapses under its own weight, squeezing mass into a volume so tiny that the laws of physics start sweating. The result is a gravitational psychopath so intense that even light gives up trying to escape. Gravity that warps the clock. Here's where it gets fun and existentially destabilizing. According to Einstein's general relativity, gravity isn't just a force, it's the curvature of space-time itself. The more mass you pile into one spot, the deeper the dent in the fabric of space-time, and black holes make Grand Canyon-level dents, except vertically, and in time as well as space. As you get closer to a black hole, time starts to stretch. Your seconds become minutes to someone watching from afar. Closer still, and you enter deep time dilation. The clock on your spaceship ticks once while a century slips past outside. From the outside, you're moving in slow motion, not because you are, but because space-time itself is leaning so hard that your timeline just stretches. The freeze frame illusion. Get too close to the event horizon and something weird happens. You start to vanish, not suddenly, but gradually. The light coming off your ship gets stretched into redder and redder wavelengths. To a distant observer, you never actually cross the event horizon. You freeze, suspended in a gravitational limbo, red-shifted to the point of invisibility. From their point of view, it looks like you're stuck at the edge of time, caught mid-fall forever. It's the space equivalent of being caught in the world's slowest screenshot. But here's the thing, you don't feel that. For you, time keeps rolling. Wormholes and time machines. Let's say you're fed up with long-haul flights and instead of boarding a plane to another city, you wish you could just step through a doorway and bam, you're there. That's basically the dream of a wormhole, but not just across space, across time. Welcome to the theoretical playground of Kip Thorne, a physicist so good at bending space-time with math that Christopher Nolan literally hired him to keep Interstellar scientifically legit. Thorne didn't invent wormholes, but he made them terrifyingly real. On paper, anyway. Wormholes, in theory, are tunnels through space-time, cosmic cheat codes that connect distant points in the universe. Picture space-time as a sheet of paper. If you draw two dots far apart and fold the paper until they touch, that's a wormhole. Enter one end, pop out the other. No billion light-year commute required. Now bend that idea even further. If one end of the wormhole sits near a black hole and the other chills far away in normal space, time begins to pass differently at each end. That's time dilation. The mouth near the black hole experiences time in slow motion compared to the one further away. Keep this setup stable and voila, you've built a time machine. Walk in the slow end, exit the fast one, and you've traveled to the future. Go the other way? You've jumped back in time. It's the universe's version of stepping through a door before you've even entered the building. But that's where the headaches begin. Of course, the moment you allow time travel, the laws of logic start setting themselves on fire. Grandfather paradox. Go back in time, stop your parents from meeting, and boom, you never exist. But then, how did you go back in the first place? Now you've begun to mess with causality. Bootstrap paradox. Say you go back and hand Shakespeare a copy of Hamlet. He copies it down, publishes it as his own, and centuries later, you read it, memorize it, and travel back to give it to him. So, who actually wrote it? No origin, no cause, just a loop where the effect creates the cause. Headache paradox. The point where your brain just gives up. Because if you can go back in time, what can't you break? And then there's a paradox for you. If you went back in time and stopped yourself from watching this video, are you still watching it right now? Subscribe and let's unravel the time travel madness together. So, can wormholes be time machines? Mathematically, yes. Theoretically, maybe. Practically, not a chance in hell. Well, not yet. To build one, you'd need a traversable wormhole, never seen one. Exotic matter, never found any. Precision timing and shielding to survive passage, and no paradoxes that unravel causality like a cheap sweater. And even if you pulled it off, the moment you tried to use it to go back in time, the universe might slam the door shut. Some physicists believe that there's a built-in mechanism, like Hawking's chronology protection, that ensures time travel never actually works, no matter how clever you get. The problems, like all of them. So you've survived the wormhole roller coaster without imploding, collapsing space-time, or collapsing from sheer theoretical whiplash. Now you want to actually travel through a black hole? Let's talk about what's waiting for you on the other side. Spaghettification. You ever tried pulling chewing gum apart slowly? Now imagine the gum is you. That's spaghettification. It's physics basically saying, you're getting torn apart, but slowly like a thread. It happens because gravity near a black hole doesn't just pull you, it pulls differently on different parts of you. Your feet, closer to the center, get tugged harder than your head. The result is you're stretched like spaghetti. The technical term is tidal force, but don't let the calm name fool you. These aren't gentle ocean tides. They're more like the gravitational equivalent of two trucks pulling you in opposite directions. For small black holes, you'd be torn apart before you even hit the event horizon. But for supermassive black holes, like the one at the center of our galaxy, you might actually pass through the event horizon without noticing, only getting pulverized further in. Hawking radiation, the universe's slow burn. Let's say you somehow built a wormhole, kept it stable, defied paradoxes. Now you want to park one end near a black hole. Well, there's a ticking time bomb attached. Hawking radiation. Stephen Hawking proposed that black holes slowly evaporate, not explode, just simmer away into nothing. Slowly bleeding radiation till it's gone forever. If Hawking radiation does erase black holes, what happens to the stuff inside? The person. Some say it's encoded in the radiation somehow. Others think information clings to the event horizon. Some propose holograms. Others, firewall death. But here's the brutal truth. If you fall in hoping to time travel, you might just get erased from the universe. So, do you actually time travel or just die in style? Let's recap your odds. Survive spaghettification? Only if the black hole's big enough. Survive Hawking evaporation? Maybe, if you wait a few trillion years. Avoid paradoxes? Possibly, if the universe secretly self-edits. Even if you do all that, if you stabilize wormholes with exotic matter we've never seen, slip past the event horizon without being shredded, and thread causality like a master seamstress, you still face the final boss, the breakdown of known reality. Because the closer we get to time travel, the more the universe throws quantum bricks at us. We don't just lack the technology, we lack a working manual for how space-time really works. The hope and the math. Let's say you're still alive and still asking, but what if? Well, here's your glimmer of hope, served with a side of impossible math and theoretical duct tape. Kerr black holes. Regular black holes are more of child's play. The real party is inside a Kerr black hole. Unlike a boring, non-rotating Schwarzschild black hole, which is just a cosmic no-fun zone, Kerr black holes spin like a record player. Most black holes in the universe are Kerr types because the stars that created them were already spinning. Conservation of angular momentum says, if you spin while you die, your corpse spins too. This rotation brings some juicy side effects. The ergosphere, a swirling limbo just outside the event horizon where standing still is not an option. Space itself is being dragged around the black hole like taffy in a hurricane. If you're in this zone, you're orbiting whether you like it or not. Frame dragging. Because why shouldn't space-time behave like a drunk carousel? Everything near a Kerr black hole gets twisted and dragged. Your GPS would scream. Inner and outer event horizons. Because one layer of doom wasn't enough. The inner horizon opens the door to some real sci-fi scenarios, like time travel, alternate timelines, or just endless screaming in math. And the Penrose process, the ultimate cosmic hustle. It might be possible to steal energy from a Kerr black hole by tossing objects into the ergosphere and catching them as they get flung out with extra juice. It's like tricking a celestial slot machine. Kerr black holes are more than just astrophysical metal albums in space. They're the best shot we have at bending space-time hard enough to poke a hole in causality. Inside a Kerr black hole, the singularity isn't a point, it's a ring. Think of it like the cosmic version of a hula hoop, but made of infinite density and existential dread. In theory, if you fall just right, you could thread the ring and avoid being crushed by gravity. Some solutions to Einstein's equations suggest you could pass through this ring into another universe or time period, or straight into the blank pages of physics' unwritten chapters. The catch is that this is purely mathematical. No one knows what's actually inside a Kerr black hole. It could be a time tunnel, or a glitch in reality that turns your atoms into jazz. Tipler cylinders. Next we have the Tipler cylinder. Imagine a spinning rod, except it's infinitely long, rotating near light speed, and warping spacetime into a loop. The idea is that if you orbit this cylinder just right, you could enter a closed time-like curve. That's physics speak for you leave and come back before you left, like sending an email and getting a reply before you hit send. The problem is that the Tipler cylinder needs to be infinitely long, massively dense, and rotating like a blender on meth. Oh, and it probably collapses under its own gravity, shreds itself with its own frame dragging, or requires negative energy to even function. Stephen Hawking politely called BS on this by pointing out that a finite Tipler cylinder needs an infinite supply of negative energy, which is like saying you can build a time machine if you have a unicorn battery powered by regret. Could aliens do it, though? Sure, if they figured out how to generate stable wormholes, harness exotic matter, and navigate gravitational chaos for wormholes. We, however, are very much not there. Humanity is like a toddler with crayons trying to redraw the schematics of a nuclear reactor. We barely survived building the James Webb Telescope without duct taping it upside down. The joke is on us, though, because the math technically allows it. Closed time-like curves? Possible. Wormhole mouths moving at different gravitational speeds? Possible. But that math doesn't protect you from getting annihilated by radiation, being crushed by tidal forces, watching the wormhole collapse milliseconds after you enter it, or violating quantum mechanics and causing reality to hard reset. So yes, the math says, maybe, but in every scenario, you're either turned into soup, erased from history, or trapped in an infinite loop of being late to your own funeral. Time travel isn't impossible. It's just not something you'll be walking away from with a souvenir mug.